Hey everyone, how it goes, and welcome back to Computer Science 146. Today, we're going to do more searching, sorting, and complexity. Oh my. In a previous lecture, we started discussing efficiency, and this is producing some desired results with little or no waste. The type of efficiency we were looking at was time and space. And we also looked at how we can start measuring efficiency. We then moved on to the concept of complexity, and this is a way that we can classify computational problems based on their difficulty. Now, in order to measure the complexity, we introduce asymptotic analysis, and this is a way that we can describe the limiting behavior of some sort of function. And also as a reminder, remember that limits in math are a value that a function approaches as the input approaches some value. We had then introduced this big O notation. This is a mathematical notation that basically means the worst case scenario, the theoretical upper bound given some amount of data in. How can we describe this function? Some very common big O complexities that were also introduced were constant, logarithmic, linear, linear-arithmic, quadratic, exponential, and also factorial. Today we're going to start applying these concepts to sorting algorithms. So our problem is, if we're given some array of integers, we have to develop an algorithm that sorts the values from smallest to largest, in other words, ascending order. One type of algorithm that we can use to sort values is called selection sort. The main idea is what you do is starting from the first index, you're looking for the first smallest value. Once you find that, you make sure that that smallest value is placed in the first index. Then you move on to the next index, finding the next smallest value. Then the next, until you're done. Looking at this, the way that we can start this out is starting from our first index. We can assume that we start here, and also that this is the smallest value. However, we need to confirm this, so we need to examine every other value. As we notice, 8 is smaller than 10, so we have found a value that was smaller. 7 is smaller than 8, so we found a new smaller value. 6 is smaller than 7. 12 is not smaller than 6, but 5 is. 11 is not smaller than 5, 9 is not smaller than 5, and so we have reached the end of this array, finding the smallest value. Now notice, the start value and the smallest value are at two different indices. Whenever this happens, we just simply swap those values, and then we move on to the next index. We know after this first run that we have the smallest value in the first index. And now starting here, we're looking for the next smallest value. Now scanning through this, we're eventually going to discover that 6 is the next smallest value. So then we swap those two and move to the next one. Now we keep doing this until the array is fully sorted. So now we need to look at the selection sort's complexity. So, first of all, we were trying to sort an array of integers in ascending order, smallest to largest. The obvious worst case is if the array was sorted completely backwards, largest to smallest, descending order. This means the smallest value, which has to be in the first index, is all the way at the end of that array. Now let's assume that the input, this array, is size n. This means to search for that smallest value is going to take n steps. But once we have that smallest value, we never have to look for it again. We now have to look for the next smallest value. Now there's one less item in this array because we've already found the smallest. We're looking for the next smallest. This means this search would take n minus 1 steps to find it. And then the next smallest, n minus 2. Next, n minus 3, etc., until we're at the last element, which will be the largest. Now we can approximate this complexity by basically looking at, we start out with this n, And then we have to add these number of steps plus these number of steps plus all of these steps all in a row. So if our array was size n, and we have to do n by n plus 1 minus n, minus 2, da-da-da-da-da, we can basically safely say that the complexity of selection sort is big O of n squared. Big O describes a theoretical upper bound. It is a function where you cannot go above that number of operations given this algorithm. Now, if you were to sum these together, all of these values, then yes, all of these values combined would be less than the function n squared. But it does not have to be exact. It is very close, but it's not exactly n squared. Regardless, this n squared is larger than what is described here, so this is a good big O complexity. Now let's take a look at a different sorting algorithm that takes a slightly modified approach. Let's look at bubble sort. The way that this one works is you check side-by-side elements one at a time. Now, if a value at an index is larger than the value of its neighbor, its I plus 1, then you need to swap those values. You continue doing this until you have made no swaps. Let's take a look at this example. If we start out here, 10 is greater than 8, we need to swap those values and then move on. 10 is greater than 7, we got to swap those values, move on. 10 is greater than 6, swap those values, move on. 10 is not greater than 12, move on. 12 is greater than 5, swap them, move. 12 is greater than 11, swap them, move. 12 is greater than 9, swap them, and we're done. Now you may notice that this is the largest value in the array. The main concept of bubble sort is you bubble up largest values. So after the first run, we have found the first largest value and put it in the last index. Then when we run it again, it'll find the next largest, then the next, then the next. Effectively, bubble sort is kind of the reverse of selection sort. So after a couple of steps, we're eventually going to end up with a sorted array. So now we got to look at the bubble sort's complexity. And once again, the worst case can be assumed to be in descending order. The largest value is first, smallest value is last. Now, in order to bubble up that largest value, we're going to have to take n swaps in order to get there. And then when we're looking for the next largest value, well, since we found the largest, we don't worry about that one, and that's going to take n minus 1. And then n minus 2, n minus 3, etc., etc. Once again, if we sum up all of these operations together, we can sufficiently say that this is big O of n squared. So the big O of selection sort and bubble sort was n squared, and theoretically, they have the exact same complexity. So then the question is, can we do better? Can we sort more efficiently? Now let's describe a more advanced sorting algorithm called merge sort. The idea behind this is merge sort is a divide and conquer algorithm. This requires us to use recursion in order to solve it, and the first step is we recursively cut the array in half until we reach single elements. Then we start merging together smaller arrays into sorted small arrays, then use the smaller sorted arrays to sort together the larger array. So if we're given this array in this example here, let's go ahead and cut off the index and the value. That way we can just see this a little bit better. Just keep in mind that the top row are the indices, the bottom row are the values. So starting off with this 8-element array, we split this in half. And then we split the halves in half. Then we split the half-halves into halves. And now we're down to singular elements. Now we start the merge procedure. Each one of these have to be merged together into an array. So when we have this, keep in mind, if we always correspond this as being the left array, this as being the right array, and this being the merged array, then keep in mind we're going to use the indices I only on left, J only on right, and K on the merged. The merging procedure goes as follows. You look at the left and right array, select the smaller of the two values, add it to your merged array. So in this case, 8 is smaller than 10, so we add this to our merged array. Now we have no more elements left in that right array, so we have to add everything that is left over here, which is just 10, and so we add that to our merged array. Notice this array is sorted. We're going to use this solution to further sort this. Now moving over here. If we're merging these together, 6 is less than 7, and basically the same thing happens here, where 6 is added first, we're done with that right array, so we have to add the rest of the elements from the left array. Merging these together, we basically get all of these different results. Now we're not finished because we have to continue merging the arrays together. Now we get to this one. Once again, if we consider this to be left, right, merged, IJK, then once again we just select the smaller of the values. 6 is less than 8, so we add 6, increase the index. 7 is less than 8. Add it there, increase the index. Now we've exhausted all of the values in our right array. Now we just simply add the left array to it. Now the big thing to point out is we no longer have to compare this value versus this value. We already did that. This array is sorted. All we have to do is move those values in there. Now we repeat the same procedure. 5 is less than 9. 9 is less than 12. 11 is less than 12. We're done with the right, add the left, and now they're merged together. And notice, this array is sorted, and this array has already been sorted. Finally, we merge these arrays together. 5 is less than 6. 6 is less than 9. 7 is less than 9. 8 is less than 9. 9 is less than 10. 10 is less than 11. Now we've exhausted everything in the left array, add everything from the right, and now we have a fully sorted array. By using this divide and conquer approach, we avoided rechecking the same values over and over again. By solving the small problem, sorting a very small array, and then using that solution to solve the big problem, we've effectively used recursion in order to develop this sorting algorithm. Now, let's see how this looks in code. As we can see, we already have our project set up and ready to go, and we created our class for our sorting algorithms. The first thing that we're going to do is create the public static void merge sort. And we're going to merge sort this int array A. Now the implementation of merge sort I'm going to go over is very verbose. The thing is, there are optimizations that can be made to this to make it more efficient in practice. However, I want you to fully understand what's going on here, so I'm going to go into a little more detail. First thing, we're going to create an int size and have that be a.length, the size of the array. Now, as we are first subdividing each one of the arrays in half, if we discover that this size is less than 2, this means we have an array of a single element we need to return. Now, if that's not the case, we need to calculate the middle index. In this case, what we're going to do is int mid is equal to the size divided by 2. Then, we're going to construct two arrays, a left and a right, and populate them with the values that are found inside of A. In order to do this, we need to calculate the size of the left and the right array. So int left size is equal to the mid index. Int right size has to be the remaining values, so we just take this size and subtract it from the mid. Once we have the sizes, we can then create the arrays. Int array left is equal to new int left size. And int array right is equal to new int right size. Now we've constructed these two arrays, but we still need to populate them with the values that's found in A. Let's focus on the left array. For int I is equal to 0, I is less than the midpoint, I++. Left at I is assigned to A at I. So cutting this array in half, now we've populated this with everything on the left-hand side of this midpoint. So next we have to do the same thing for the right-hand side. We're going to do this a little differently. For int I is equal to the midpoint. I is less than the size I++. Inside of here, that way we avoid an index out of bounds exception, we're going to take right at index I, but minus mid. So looking at this from the first run, I is initially assigned to the midpoint. If the midpoint minus the midpoint is equal to 0, this means we're accessing the first element in right. Then we just need to simply assign this value to the value found in A. So now what we have done is we have split this array A into a left and a right, and then populated it with all the values. We then need to recursively go through and continue to subdivide these until we get those singular elements. So this is where we recursively call merge sort on the left side and merge sort on the right side. Now, once we've gotten down to these singular elements, the thing is, we're going to eventually come back from this recursive call and this recursive call. Once we have done that, what we need to do is merge them together. I'm going to separate this out into a different method. Entering down, we're going to public static void merge an int array left and an int array right into an int array A. Now, so I don't accidentally forget this, we need to call this merge after these merge sorts. So merge the left and the right into the array A. Now we need to develop this merge method. What we're going to do is very similar to what we saw in the example. So first, we're going to just store some quick values. Int left size is equal to left.length, and also int right size is equal to right.length. Now in the example, we directly corresponded certain indices with certain arrays. So the first one, int I is equal to 0. This is going to be the left array's index. Int j equals 0, and this is the right array's index. Int k is equal to 0. This is the merged array's, in other words, the array A, index. Now that we have these in place, what we have to do is follow that merge procedure. What we're doing is examining the values on the left and right hand side, selecting the smallest of the values and adding that to A. We do this until we've exhausted either all the elements on the left or all the elements on the right. So then while I is less than the left size and j is less than the right size, then we haven't exhausted all the elements in either the left or the right array. Now, while we're doing this, if we discover the left at index I happens to be less than or equal to right at index j, this means we found a smaller value in the left array. We need to add this value to the merged array A. A at index k is equal to left at index I. Then we increase I++ and then k++. Now, if this was not true, this would indicate that the right value was smaller than the left. So in this case, we have to add the elements from the right array into A. A at index k. Once again, keep in mind, I only corresponds to left, j only corresponds to right, k only corresponds to the merged array A. So A at index k is assigned to right at index j. Then we increase j++ and k++. We're not quite done, because in the example we saw several times that we exhausted all the values in the left array or the right array. So now we have to take those values into account by adding the rest of them back into the array A. While I is still less than the left size. If this is true, this means we exhausted all of the elements in the right array and there were still some left on the left. In this case, we simply assign A at index k is equal to left at index I. Once again, I++ and k++. We do the same thing for the right. So in other words, maybe we exhausted all the elements in the left array, and that means while j is still less than the right size, then we need to add A at k equal to right at j, increase j, increase k. And so this is the merge method for merge sort. Let's now test this out with the example that we used before. Scrolling all the way back up to the top. First thing we're going to do is create an int array, and let's just call it array. Now we're going to assign this to the values that we found in our problem. So it's going to be 10, 8, 7, 6, 12, 5, 11, and 9. Now we're going to merge sort this array. In order to confirm this works, we're going to print out all of the values. So for each int I in array, we system.out.println I. Now let's see if this works. And sure enough, we get a sorted array. One other quick thing to point out that has nothing to do with merge sort. Notice that we created this int array here. We then passed this in via parameter, and the array came back sorted. Notice that merge sort does not return an integer array. The thing is, in Java, arrays are considered object types. The thing is, this value is a reference to the actual array A. As we have modified the elements inside of here, and this was only passed by a reference, this does modify the array that we passed in. So there was no need to actually create a return value here because we know this pass by reference language, Java, does this for us. That was a lot of code, so let's figure out if it was worth doing all of that for this sorting algorithm. Now, once again, we can assume that the worst case scenario for this is everything is sorted in descending order. The operations that we're looking at are splitting and merging. Now, one of the ways that we can calculate its complexity is by looking at what happens at the data. First of all, if we were to visualize this, we start out with this array with n values. Then we cut that in half, in half, in half. Then those halves into halves, and those half-halves into halves, until we get down to these singular elements here. So how many times are we splitting this array up? Assuming that we have n elements, we can measure the height here, and understand that this is going to be log base 2 of n splits. Now at each one of the levels, we are merging those values back together. As you can see right here, if we add together all of these values, this is going to correspond to n. n half plus n half is also n. n quarter, n quarter, n quarter, n quarter is all n. If we add each one of these rows together, when we merge them, it's effectively going to be n. Now we can use this to approximate the actual complexity of merge sort, which is n by log base 2 of n, so we can say that it is big O n log n. Is this better than n squared? Absolutely. So the theoretical time complexity for merge sort is better than both selection and bubble sort. Now let's take a look at a different sorting algorithm, a very popular one called quicksort. The main idea about quicksort is you pick an arbitrary value that you call the pivot. What you then do is determine all of the values that go on the left-hand side of the pivot, in other words, less than, and all the values on the right-hand side greater or equal to the pivot. Once you have established all of those values, you then split the array based on where that pivot position is, and then continue this procedure recursively. Let's see an example of how this works. So let's say, for example, we're always picking the last element as our pivot. And remember, this isn't the index, this is the value that we're looking at, so we're looking at the value 9 as our pivot. Now, over to the side, we have two indices, I and j. So the idea is if the value at index j is smaller than the pivot, then we swap the values at I and j and then increase the I by 1. So starting out with this example, 10 is not less than 9, we move j forward. Now 8 is less than 9, so we swap the values found at I and j, which end up looking like that. Now we increase the I, so it looks like this. Moving this forward, 7 is less than 9, which means once again we have to swap the values at I and j, so now it looks like this. We then increase the I. Moving the j forward, 6 is less than 9, we have to swap the values, increase the I. Moving j forward, 12 is not less than 9, move it forward. 5 is less than 9, swap the values at I and j, then increase the I. 10 is greater than 9, 11 is greater than 9, and now we reach that pivot value. 9 is not less than 9. So once we're outside of that, what we then must do is swap the values at I and the pivot. And now what we have here is the value 9, where we have the left-hand side of this array is all the values less than 9, and all of the greater values to the right-hand side. This I right here indicates where the pivot should be. Now we recursively do the exact same thing on the left and the right-hand side of those arrays. So focusing on the left-hand side, we start here. As we are picking the last value as the pivot, what we're then going to do is follow the same procedure. Whenever we discover a value that is less than the pivot, we swap the values at I and j. So 8 is not less than 5. 7 is not less than 5. 6 is not less than 5. 5 is not less than 5. And so, as we've reached the end of this, we now have to swap the value found at the pivot with the value found at I. And so that's where 5 belongs. Now we recursively do that on the arrays here. But here's the trick. There is no left array. There's only a right. So we recursively do this on the right array, once again, selecting the pivot as the last value, and then running this one more time. 7 is less than 8, but notice that I and j reference the same value. So in fact, what would happen is we're swapping the value with its exact same value, but ultimately what happens is we move this I and j together. Now 6 is also less than 8, and the same thing happens. I and j reference the same value, we'd be swapping the same value, so ultimately we just move it forward. Now we have this I and j that's right here at the pivot. And we still do the same thing. We swap the value I and j with the pivot value, but since it refers to the same thing, it just remains right there. And in fact, 8 was where it should have been all along. Now once again, we have a case that we have split this. We have one side but not the other. But in this case, we have the left-hand side and no right-hand side. Repeating this procedure. 7 is greater than the pivot, so we move j forward. Now, 6 is not less than 6. We're done with this. We swap the pivot value with the value found at I, and so now 6 is there. Once again, we don't have a left array, we only have a right. Now, as I and j reference the same value, and there's nothing to the left and the right of it, we can confirm that this is where that value should be. Now, once we have done all of that, we recursively go back and finally get to the right-hand side of this array that was initially found from our first step when we partitioned it. Now we focus on the right-hand side. 10 is less than 12, we move I and j forward. 11 is less than 12, move I and j forward. 12 is not less than 12, but is the last thing, so we switch the values, and ultimately, yes, it should be right there. Now we don't have a right-hand side of this, we only have a left. So starting here, 10 is less than 11, I and j move forward. Now since we're here, we only have one element, it's where it should be. We don't have a right-hand side, we have a left. There's only one element, and that's where that should be. Let's see how quicksort works in code. Now scrolling down a little ways, we're going to develop quicksort down here. I'm first going to create a public static void quicksort with an int array a. Now I'm going to override this method. Public static void quicksort with int array a with a start index and an end index. Now from our initial method, what we're going to do is call quicksort using the array a, starting from index 0, and then going to a.length -1. I only wrote this, that way we can just pass the single array in here, and then this does the calculation based on the indices. Now once again, we're going to be using recursion. We have to worry about that halting condition. If the start is greater than or equal to the end index, we simply need to return. Now otherwise, we need to get that pivot value. We do this by partitioning A based on its start and its end. Creating another method, public static int, partition. We're going to partition this int array A with a start index and an end index. The value that we're going to return is the index I, and that's how we determine where we split this, where we partition this. So we're going to first start by selecting int pivot. This is going to be A at the end index, the last value in this array. To make this simple, we're also going to create an int I and assign that to the start index. Then, for int j is equal to the start index, j is less than or equal to the end index j++. If we discover A at index j is less than the pivot value, that's where we need to swap those. So we create an int temp, assign it to A at index I. A at index I is equal to A at index j. A at index j is equal to temp. And also we increase the I by 1 whenever we do this. Now outside of that for loop, we finally reached that pivot value. This is where we have to swap that out as well. Int temp is equal to A at index I. A at index I is equal to A at the end index. A at the end index is equal to temp. And finally, we return the value found at I. So once we go through all of this, the I corresponds to the index where the pivot is. Now we don't have to worry about that value. We can sufficiently split this array A in half and repeat the same procedure. Going back to our method, we can then calculate int pivot is equal to partition with A, start, and end. Then we can recursively call quicksort on A from start to the pivot -1, so this is the left-hand side, and quicksort with A, starting from the pivot +1 to the end, the right-hand side. And this is one implementation of quicksort. Let's see if it works. Now modifying this, we're going to change it from merge to quicksort. And let's see if it works. In fact, it does. Let's take a closer look at quicksort and figure out what its complexity may be. Now, quicksort has some strangeness built into it. It turns out with the version of quicksort that we've gone over, the worst case scenario is if the array had already been sorted. In other words, if it was in ascending order. Now, this is assuming that we always pick the last element as our pivot. Let's see what happens here. If we start here with our I and j, and our pivot is our last value, well, what we do is whenever we find a value that's smaller than the pivot, we swap those values at I and j, and then increase I, and then increase j. Well, 5 is less than 12, we swap that, and it remains the same, move it forward. 6 is less than 12, move it forward. Move it forward, move it forward, move it forward, move it forward. Now we're here. 12 is not less than 12, but the last thing that we do is swap the pivot value with the value found at I. So this effectively remains in the same place, but now we're done here. As you can see once again, there was not a right array, only a left. And that left array is of size 7, which is 1 minus the total amount 8. So we're going to notice that the same thing happens here. 5 is less than 11. 6 is 7, 8, 9, 10, 11, so we stop right there. And 11 is where it should be. We partition this. Once again, there is no right-hand side, only the left. And now this is 6 elements. 2 minus the total elements here. As we keep going through this, we're going to notice that in order to move these I and J's on the first time, we have to move that n number of spaces, assuming this array was of size n. Then we have to move n minus 1 spaces to get to the next value, then the next, then the next, then the next. So looking at this in the worst case, if we add all of these together, the big O for quicksort is n squared. This means in the worst case, quicksort is not better than merge sort, and it has the same time complexity as bubble and selection sorts. Now to mention this, quicksort is commonly implemented in a lot of computing software. So why do we use quicksort over merge sort, which always is going to be better at the n log n time complexity? Of course, there's more to the story than just the time complexity, because we can look at the worst time complexities of merge sort, which is n log n, versus quicksort, which is n squared. However, that is only one side of the story, because we can also look at another mathematical notation called big theta. This corresponds to the average time complexity. It turns out merge sort is also still n log n. However, with quicksort, the cases where we would get an n squared time complexity is kind of rare. And if we were to pick the pivot in a more sophisticated way, we can ensure that the average time complexity for quicksort is n log n. Now, in addition to this, merge sort is far worse when it comes to space complexity. You need more memory in order to run merge sort. However, quicksort uses far less space complexity and has a better average time complexity. Ultimately, what this comes down to is a trade-off. Are we going to spend potentially more time calculating this while using less space, or are we going to use more space, thus using less time to do the same thing? We're going to take some of these concepts and now start applying this to our data structures. That way we can now create more efficient data structures. With all that being said, I'll see you next time.